This video shows a Kriging-based self-adaptive cloud controller. This is joint work with Alessio Gambi, Giovanni Toffetti, Fabrizio Pastore, and Mauro Pezzè from the University of Lugano. As a demo application, we consider the SunGrid engine, a simple service composed of a singleton master node that acts as a load balancer and a configurable number of executor nodes. Applications running in the cloud can be automatically adapted to different execution conditions. The following experiments have been executed on the Reservoir cloud architecture. Reservoir allows the dynamic activation of virtual machines and allocation of resources to them. Here we see the administration interface of Reservoir. On the top left, we see how the incoming service requests change during the experiment. On the top center, we see the length of the job queue on the master node. And on the top right, we see the service control events. Below, we see the average response time. On the bottom, we see the workload widget that allows us to simulate different workload conditions, and a control widget that allows us to manually allocate or deallocate executors. The service level agreement for this application requires a response time of 120 seconds or less for 90% of the requests in a 5-minute window. We can see that without dynamic control, the example workload leads to an SLA violation. We now show how a manual control can reduce SLA violations. When the service control timeline reports an SLA violation, the operator can manually activate new executor nodes to serve the peak of requests. We can see in the service control timeline the SLA violation events, followed by virtual machine creation events. We first see the creation requests and then the activation of the virtual machines. Now, with more executor nodes, the system is able to process more requests, reducing the queue length and therefore reducing the response time for incoming jobs. However, manual execution is slow, error-prone, and does not scale to large systems and large sets of control variables. We now introduce the automatic Kriging controller. As all surrogate models, Kriging models must be trained. In this example, we use a training workload that samples different incoming requests and different lengths of the job queue for a single executor configuration. The training phase shapes the model as visible in the top right window. The model is then later used to predict system responses. In this simple case, the response time grows linearly with both the queue length and the rate of incoming requests. We now show the autonomic Kriging controller. The controller automatically reacts to different load conditions according to the predictions of the Kriging models that we just trained. When the workload increases, the autonomic controller automatically creates new virtual machines, as we can see on the automatic control widget. Virtual machines are timely activated according to the predictions of the Kriging models. This way, the system does not experience SLA violations. When the workload decreases, the autonomic controller automatically scales down the number of executors so as to reduce costs.